NASA successfully saves JunoCam after radiation damage through a annealing technique. Imagine a tiny camera holding its own against the brutal radiation storms around Jupiter. That's the incredible story of how NASA's Juno mission turned a potential disaster into a triumph with JunoCam. This isn't just about space tech. It's about human ingenuity saving the day millions of miles away. And it's got me hooked on how one clever fix could change everything we know about exploring the solar system. Let's start with the basics. The Juno spacecraft blasted off in August 2011 as part of NASA's New Frontiers program, which is all about bold missions to uncover the secrets of our solar system. Originally, it was designed for a 7-year adventure, including a long 5-year journey just to reach Jupiter. But here's the thing, missions like this often get extended if they're performing well, and that's exactly what happened. Juno is still circling Jupiter today, racking up years of valuable data with its suite of scientific tools. One of those tools is JunoCam, a sophisticated visible light camera that acts like a telescope, snapping pictures that help scientists study Jupiter's atmosphere, storms, and even its moons. Now, Jupiter isn't your average neighborhood. It's surrounded by intense radiation belts that are way harsher than anything near Earth. Think of it like a cosmic particle accelerator constantly bombarding anything in its path. Many experts predicted that JunoCam wouldn't last long under this onslaught, expecting it to fail after just a few dozen orbits. Sure enough, after surpassing its initial mission goal of 34 orbits, signs of damage started showing up in the images: blurry spots, distorted colors, and overall degradation that made the data hard to use. But here's where it gets controversial. While the damage was clear, pinpointing the exact problem wasn't straightforward, and that led to some heated debates among engineers about whether a fix was even possible. After digging into the issue, the team discovered that the image sensor itself was still in good shape. That's the part that actually captures the light. Instead, the culprit was a voltage regulator in JunoCam's power supply, which was getting scrambled by the radiation. Radiation can mess with electronics by dislodging atoms in the materials, creating defects that cause components to malfunction over time. It's like how rust can weaken metal on Earth, but in space, it's happening at warp speed due to high-energy particles. Desperate for a solution, the engineers turned to a technique called annealing, which might sound familiar if you've ever heard about it in cooking or crafting. In simple terms, annealing involves heating a material to repair damage by allowing atoms to realign and heal imperfections. For JunoCam, they cranked up one of the camera's heaters to a toasty 25 degrees Celsius. That's warmer than its usual operating temperature, and held it there. At first, this seemed like a miracle. The image quality shot up dramatically on the next few orbits. But, as you might guess, the improvement didn't last, and the degradation crept back in. And this is the part most people miss. Sometimes, a quick fix isn't enough in the face of persistent challenges, which is why the team didn't give up. Before Juno made a close flyby of Jupiter's fiery moon Io, a region even more radiation intense, the engineers decided to go all out. They amped up the heater even more, pushing it to higher temperatures, and waited with bated breath. Over the course of a week, this more aggressive annealing did the trick, restoring JunoCam to near-perfect condition. It's almost like giving the camera a spa day in space, but with serious scientific implications. Now, the team is experimenting with this approach on other instruments aboard Juno, and it could serve as a blueprint for future missions. For instance, if this works broadly, spacecraft designers might start incorporating similar self-healing mechanisms, potentially extending the life of probes sent to other harsh environments, like Saturn or even beyond our solar system. Of course, not everyone is on board with this hack. Some critics might argue that relying on heat-based fixes could introduce new risks, like overheating other components or masking underlying issues that could crop up later. But others see it as a stroke of genius, proving that creative problem-solving can outmaneuver the universe's toughest challenges. What do you think? Is annealing a game-changer for space exploration, or does it feel like a risky band-aid solution? I'd love to hear your thoughts in the comments. Share whether you'd trust this method on a mission to Mars, or if you have a better idea for combating space radiation. NASA overheated JunoCam in space. Epic fix saves Jupiter and Io views. NASA's Juno spacecraft, equipped with the JunoCam visible light camera, has achieved remarkable feats while orbiting Jupiter, despite initial expectations of a short operational lifespan. Originally intended to function for only 8 orbits, this resilient camera has impressively completed 46 orbits before encountering significant challenges. As it entered its 47th orbit, the camera began to exhibit signs of radiation damage, a known risk given the harsh environment surrounding Jupiter. This damage posed a serious threat to one of the few instruments capable of capturing images of Jupiter's dynamic storms and its intriguing moons. Engineers at NASA's Jet Propulsion Laboratory identified a malfunction in the camera's voltage regulator, likely caused by the intense radiation fields that Juno must navigate. With the spacecraft situated nearly 600 million kilometers from Earth, replacing any hardware was simply not an option. In a bold move, the team decided to increase the temperature of the camera as a potential solution. This process, known as annealing, involves heating a material and then allowing it to cool, which can help to alleviate microscopic defects. Utilizing the only heater available on JunoCam, engineers raised the temperature to 77 degrees Fahrenheit. This strategy proved successful temporarily, as the camera began producing clear images once again. However, by the time the spacecraft reached orbit 55, the issue of image corruption resurfaced. With a crucial flyby of Jupiter's volcanic moon Io approaching, the team faced a pressing need for another fix. With limited options available, they decided to push the heater to its maximum setting. For several days, it seemed uncertain whether this gamble would pay off. Yet, just before the anticipated December 2023 flyby, the camera's images regained clarity. JunoCam's revitalized capabilities allowed it to capture stunning details of Io's North Polar region, revealing mountain blocks covered in sulfur dioxide frost and previously uncharted volcanic flows. This critical fix not only salvaged the flyby, but also opened new possibilities for spacecraft maintenance techniques. The annealing method has since been applied to other instruments aboard Juno, and while NASA has not disclosed all the outcomes, they believe it is influencing how future missions will approach resilience in space. Scott Bolton, the principal investigator for Juno, remarked, "We're learning how to build spacecraft that can live with radiation. That's going to benefit everything from Earth orbiters to defense and deep space probes." Currently, JunoCam has successfully navigated 74 orbits. However, as the mission delves deeper into Jupiter's radiation belts, image noise is beginning to reappear. The question remains whether another repair will be feasible or worthwhile. For the time being, NASA's innovative remote repair strategy has provided invaluable time, data, and a rare glimpse into one of the solar system's most extreme environments. This article was authored by Ben Ward, who holds a degree in English Literature and Language from the University of Bristol. With a strong background in analytical news writing and a passion for space exploration, his work emphasizes the interplay between science, history, and language. He approaches space journalism with a commitment to accuracy and is particularly interested in how the actions of private companies, government agencies, and scientific organizations shape the future of space exploration. Outside of writing, he avidly follows developments in geopolitics, aerospace, and planetary science, contemplating how humanity's presence on Earth impacts realms far beyond our planet. NASA's Hail Mary fix: saving JunoCam from Jupiter's radiation hell. Imagine facing the harshest radiation environment in our solar system while hundreds of millions of miles away, desperately trying to keep a camera alive to capture groundbreaking images. This is exactly what NASA's Juno spacecraft endured on its mission to study Jupiter. Launched back in 2011 to uncover the mysteries behind Jupiter's formation and evolution, Juno has been journeying through some of the most extreme planetary radiation fields ever encountered. But here's where it gets controversial. In December 2023, Juno's JunoCam, a color camera designed to capture visible light and located outside the spacecraft's radiation shield, started showing signs of damage. The mission team had just a narrow window to find a fix remotely before missing an invaluable opportunity to photograph Jupiter's volcanic moon, Io. The solution came down to a surprisingly straightforward technique: a kind of Hail Mary call from 370 million miles away that saved the camera, heating the instrument and then letting it cool down slowly. Essentially, it was a process called annealing, which involves warming a material to repair microscopic radiation damage before gradually bringing its temperature back down. While it sounds simple, this method isn't commonly attempted on spacecraft instruments operating so far from Earth. To give some background, mission scientists had expected JunoCam to withstand Jupiter's punishing radiation for about 8 orbits. But the troubling signs only surfaced much later, around Juno's 47th orbit. The team pinpointed damage to the camera's voltage regulator, a key component controlling its power supply. At such a staggering distance, options to intervene were extremely limited, prompting the team to experiment with annealing. Jacob Schaffner, the JunoCam imaging engineer from Malin Space Science Systems, shared insights on the risks involved. We knew annealing can sometimes change materials like silicon at a tiny, microscopic scale, but we weren't sure it would actually fix the damage. They increased the temperature inside the camera to 77 degrees Fahrenheit, 25 degrees Celsius, much warmer than JunoCam's usual operating climate, and waited nervously for any sign of improvement. Surprisingly, this initial annealing step allowed JunoCam to continue capturing crisp images for several more orbits. But Jupiter's relentless radiation soon took its toll again. By orbit 55, straightforward issues like streaked images and noise corrupted the photos. Attempts to clean up these images through digital processing failed to restore quality. And this is the part most people miss. Facing a looming close flyby of Io, the mission was at a crossroads. Michael Ravine, JunoCam's lead instrument specialist, described the desperate strategy. The only option left was to max out the heater and perform a more intense annealing process to see if it could save the camera. Initially, this aggressive approach seemed fruitless. Yet, just days before the critical Io encounter, the picture quality dramatically improved. On December 30th, 2023, JunoCam delivered stunning, detailed aerial views of Io's North Pole, capturing volcanoes never documented before. This achievement was significant enough to be showcased at the prestigious IEEE Nuclear and Space Radiation Effects Conference in Nashville on July 16th, a clear testament to the ingenuity and persistence of the Juno team. Although the camera's image degradation recurred by the 74th orbit, the experience has sparked a broader conversation in aerospace circles. Scott Bolton, the principal investigator for Juno from the Southwest Research Institute, explained, "Juno is effectively showing us how to build and maintain spacecraft that can withstand intense radiation, knowledge that will greatly benefit satellites in Earth orbit." This implies lessons learned here may influence not just future NASA missions but also commercial and defense satellite design. But here's the intriguing question for all of us. Should mission teams rely more on remote hardware recovery techniques like annealing as standard practice when dealing with radiation exposure? Or do such fixes merely postpone inevitable hardware failures? Could the extra risk taken with JunoCam's aggressive heating have permanently compromised its longevity? We'd love to hear your thoughts. Do you believe remote fixes like the thermal Hail Mary are game changers in space exploration, or are they just temporary band-aids? Drop your opinions in the comments and join the debate on navigating one of space exploration's toughest challenges.